Hello everyone, my name is Dana Vodimirova, and in this video we are going to talk about the topic of model-driven software engineering and its application in the field of quality assurance. Lately, the agile model for software development has become more and more prevalent. This model relies on continuous integration of smaller features where each new addition is implemented under the following workflow. Firstly, the idea or design for the new feature is proposed, then it is developed into working software, and this new unit in the program is tested towards inconsistencies, and in case such are present, the development step is repeated. This process continues until there are no more new changes to be made and the new feature is released or merge into the public version of the software. This model allows for great flexibility and quickly changing code base, but to ensure safety, each part of such separate components and features of the code normally unit tests are used. This type of testing ensures the quality of a single functionality under specific edge conditions. The problem with this strategy is that each new feature requires separate data to be prepared and validated for the specific test cases that have to be written for the validation of this exact new behavior. This data preparation and validation can sometimes be complex and can introduce difficulties for inexperienced developers. Sometimes the test scenario preparation contains multiple interconnected objects with specific values initialized under certain conditions, etc. The approaches we use to mitigate these problems in this work are based on model-driven software engineering. This enables the use of abstract data models for the automatic construction of the software. There are many examples of domain-specific languages that are used by experts in their respective domains to describe their work or problems they are working on. And we are just a few here are just a few such examples. We can see a structural formula of a complex chemical molecule used by chemists to represent their work, a circuit diagram used by electrical engineers, or a UML diagram used to describe human interactions. All these abstract models can be described as list of objects with their special parameters and relations, and describing them in such a way opens up possibilities for programmatically generating software based on the diagrams. Now that we know how model-driven software engineering is normally used, our goal was to explore the possibilities of its implications in the field of maintenance of already developed projects. We have developed a framework that aids the writing of unit tests by generating a way to initialize and check the whole states of the program at specific steps of its execution. To describe such states, we have chosen to work with object diagrams as they are suitable for describing concrete values and connections of the objects that are needed. Here is the abstract structure of a unit test. We first initialize the state of the project, then we apply the feature that we want to test to this initial state, and finally the output stage is compared with an expected one. Here is a more concrete example of a unit test. We have a very simple class containing a value and a method which increments this value. If we want to test this method, we firstly initialize an object of the class calculator, then we call the increment method, and we check for the expected changes in the produced object. In this example, we only need one object and we make checks for only one of its attributes. But in practice, as already mentioned, very often the writers of tests have to initialize and compare complex states of the program featuring many interconnected objects. So to narrow this complexity gap, our idea was to automate the initialization and validation steps of unit tests by generating special classes responsible for these tasks. Here's the workflow we have used. Firstly, as already mentioned, we take a simple one or more object diagrams and want to output an instantiator and check a class for each one of the given diagrams. For the realization of the project, we use the Monte-Core language workbench. So we take as an input object diagram. It is parsed via the Monte-Core parser, converting it into an object diagram abstract syntax tree structure, which we can use to extract the data, which we use to generate another model, which describes the classes we want to create in the end. This model-to-model generator uses the object diagram abstract syntax tree instances in combination with free marker templates to create and fill out the class structure that we want, and thus outputting a class diagram abstract syntax tree instance. And this class diagram abstract syntax tree instance is finally fed into the class diagram generator of Monte-Core to produce the final Java classes. Our design for the produced framework, which would instantiate and validate the object diagrams, feature the following classes. Firstly, for each individual object of the object diagram, we create an instantiator and checker. These classes are responsible for the creation or validation of which one of the individual objects with their initial primitive attributes or the assert statements for them. To create and check the connections between objects, we also generate one general instantiator class and one general checker class. They use the individual instantiators and checkers to create or check their links. And then the instantiator and checker can be used in unit tests for initialization and validation of program states. Now we can view a concrete example to make each step clear. For our example, we are using the following object diagram in textual form, which is used for the import of the program and its graphical representation. We have two objects, Alice and her address with their attributes and a link between them. The link connects Alice to her address via the connection lives at. Let's see what the already generated classes for this example would look like. Firstly, we are going to get the individual instantiators. This is the one for Alice, but we also are going to have one for the address as well. As you can see, we use the mule pattern to create an instance of Alice's class, which in our case is student, and set its attributes. For the initialization of the interconnected state, we use the instantiator for Alice and for address, and then we use the model links to connect the objects. So that is how the general instantiator looks. For the checkers, we do a similar thing. We receive here an object under test, which is compared to its expected counterpart from the object. We compare this Alice argument with the values from the model to check all the attributes of the object. So we check if the Alice that we have received is the same as the Alice from the given model. And for the object address, we are going to get an analogically generated checker class as well. Finally, for the general checker, we first check all attributes with the individual checkers, like described in the previous slide, and then check the connections from the model by applying the individual checker of the receiving object to the value of the connecting attribute. In our example, we use the address checker because address is the receiving object. Now let's see how this framework can be used in practice. Here are two object diagrams, an input and output one. We would like to take the input one, change it, and test if we have received the output model after the changes. The only one change here would be the name of the Alice object, from Alice to Bob. So the test that would be written for this situation can look as follows. Firstly, we use the instantiator class of the input diagram to receive the instantiated object. Then we change the value of the Alice name attribute. And finally, we use the output checker to see if the output model matches the resulting state after we have changed the name. In our case, this test would return no errors because we have seen that the value of Alice's name in the input model here and in the change object here are equal. So to summarize, we have developed a framework for the simplification of the development process of JUnit tests. In particular, we have automated the initialization and validation steps of unit tests via the generated classes. This framework aids the development process of unit tests, but however, defining what behaviors have to be tested and in which conditions was not in the scope of this work, but one way to achieve this case generation would be to use sequence diagrams. And if these cases can also be generated in the future, this would open up possibilities for fully automatic test generation. And here I would like to thank you for your attention.